Please like and share my videos. Subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of July 2024. The question is from the section Linear Algebra and it is related to the concepts of dimension of a given subspace. This question is from the part C, which is a multiple select question. There can be a more than one answer and it carries 4.75 marks. The question ID is 704076. This question is suitable for the aspirants of JL, DL, TS set, AP set, IIT JAM and GATE. Right. The given question is, let M5 in brackets C be the complex vector space of 5 by 5 matrices with the entries in C. M5C is a vector space of 5 by 5 matrices with the entries coming from the complex numbers, and it is a vector space over the field of complex numbers. Let V be non-zero subspace of M5C such that every non-zero A belongs to V is invertible. Read this carefully. V is a non-zero subspace of M5 over C. It's a subspace and it's a non-zero subspace such that every non-zero A belongs to A. Any non-zero matrix belongs to V is invertible. That means, who are the elements of V? They are non-zero and which are invertible. And that is a non-zero subspace of V. Right. Which among the following are possible values for the dimension of V? What is the dimension of V? What is the possible values for the dimension of V? We are given 4 options. Option 1, 1, option 2, 2, option 3, 3, option 4, 4. Right. Let's now discuss the solution of the problem in detail. We have the vector space M5 over C. Right. And given V is a non-zero subspace of M5 over C such that a matrix A is invertible for every non-zero A belongs to V. For every non-zero A belongs to V, A is invertible. So, who are the elements of V? Non-zero 5 by 5 matrices, and they are invertible. Right? Now, don't conclude anything. So, that is the definition for the subspace, non-zero subspace V. Since V is a non-zero subspace, and by definition, it has a non-zero invertible matrix, let's call it as A. Then, the linear span of A is a subspace of V. So, V is a non-zero subspace. Therefore, it has a non-zero invertible matrix, say A. Then we have considered the linear span of A, and that is a subspace of V. Right. Suppose that V has another non-zero invertible matrix B. So who can be B? That's our question. consider B plus alpha A. Alpha is a scalar. Alpha belongs to the field of complex numbers. Now, note that determinant of B plus alpha A is a polynomial of alpha of degree 5 because B and A are 5 by 5 matrices. So, it is a polynomial of alpha of degree 5. If you are convinced, it's okay. If you are not convinced, I will provide you a proof for that. So, we will discuss this after this proof. So, accept this. Accept this. So, thus, by the fundamental theorem of algebra, it has a root, say alpha naught belongs to C. So, it is a polynomial of alpha of degree 5. Therefore, by the fundamental theorem of algebra, it has a root, say alpha naught belongs to C. Thus, there exists a alpha naught belongs to C such that determinant of B plus alpha naught A is 0. So, by this, for this alpha naught, B plus alpha naught A is not invertible. Why? Determinant is 0, means it is a singular. So, it has no, it is not invertible. Since V is a subspace, B plus alpha naught A belongs to V. Right? Because it is a subspace. It's a linear combination which will be in B. Right. Right. Now, what we see is B plus alpha naught A belongs to V. And the determinant of B plus alpha naught A is 0. That means B plus alpha naught A is not invertible, but it is an element of V. What is the possibility? The possibility is that B plus alpha naught A must be 0. This means B is equal to minus alpha naught A. So, who will be B? B belongs to the linear span of A. The linear span of A. So, if you think that V has another non-zero invertible matrix B, then B belongs to the linear span of A. So, that means to say V is precisely the linear span of A only. Then what will be the dimension? And then a basis for that is A. A is the singleton A is a basis for V, and the dimension will be 1. The dimension of V over C is 1. So, that's the argument, and let's look at our options. Our answer 1, dimension of V is equal to 1 appears against option 1. Therefore, the answer to this question is option 1. And that is the detailed discussion of the solution of this problem from the section linear algebra, which is related to the dimension of a subspace. Right. This is, even though the proof is very small, that is, it's not taking much time, but this is your argument, and it is given in section C, the part C. There can be more than one answer, but surprisingly, there is only one answer. Right. So, that's the answer. The answer is option 1. And it is definitely a good question. I am sure that you have understood the solution of this problem. Before winding up this video, as I have promised to you, what will be the determinant of B plus alpha A? That is the 1. It is a polynomial in alpha of degree is equal to the order of the matrices A and B. So, for simplicity reasons, and because of the paucity of the space also, writing 5 by 5 matrices and all that is very difficult while typing. Therefore, we will prove this one. Let A, B be invertible matrices of M2 over C. Then determinant of B plus alpha A is a polynomial of alpha of degree 2. Let's look at the proof. Determinant of B plus alpha A is equal to determinant of B11 plus alpha times A11, B12 plus alpha times A12, B21 plus alpha times A21, B22 plus alpha times A22. Now expand. Use the properties of the determinants. So this will be the first determinant is B11, B12 plus alpha A12, B21, B22 plus alpha A2 plus alpha A11, determinant of alpha A11, B12 plus alpha A12, alpha 21, B22 plus alpha 22. Again, right, it will be the sum of 4 determinants you will get. So further, this one is this. This one is this, and this, and this first one, this and this one. So 2 power n, where n is the order of the matrix, 2 square. So 2 square determinants you will get. So what is the first one? The determinant of B plus alpha times determinant of B11, A12, B21, A22 plus from here alpha times A11, B12, A21, B22 plus alpha from the first column, alpha from the second column, that will be alpha square. So A11, A12, A21, A22 determinant is determinant of A. So what is this? This is a polynomial in alpha of degree 2. Why? Determinant of A not equal to 0. And that is why it is a polynomial of degree 2. It is a polynomial of alpha of degree 2 since determinant of A not equal to 0. So let's now move to our question. On the similar lines, we have the following. That is, let A be invertible matrices of M5 over C, then determinant of B plus alpha A is a polynomial of alpha of degree 5. These are 5 by 5 matrices, therefore degree will be 5. Right. So on the same lines, you can prove this also. So that's the result and a proof that I have suggested here. So we have come to the end of the discussion of this video. I am sure that you have understood the solution of this problem. I thank you one and all for watching my videos. Please like and share my videos. Please subscribe my channel if you have not already subscribed. I wish you all the best. Thank you.